All right, guys, welcome to calculus. Very exciting. Before we dive into the work, let me talk a little bit about the background and just sort of a general layout of what we're about to study. Calculus is credited to two gentlemen, Mr. Newton and Mr. Leibniz. I'm not sure if I'm pronouncing that right. They are credited as inventing calculus or being the fathers of calculus, but they certainly didn't come up with all of the material on their own. The content that makes up calculus really reaches far back before them. Different people worked on different ideas and developed it a little bit, kind of pulled on some ideas from other people. There's a lot of collaborations. People work together, people work independently. Some people worked in different languages. And so there was this whole body of work out there, and Newton and Leibniz were the first ones to kind of bring it all together and wrap it up into one book. And they made, of course, some of their own contributions and showed how things kind of play together, and cleaned up the notation a little bit. And that's one of the big issues, that since so many people worked on calculus across different languages, across different parts of the world, across different times, then it's not very cohesive. The notation is a little bit difficult to get through sometimes. So some parts of the textbook we will use. In some parts of the textbook, we will adopt a certain style of notation, and in other parts, we will adopt a different style of notation. So the notation is itself kind of a big hurdle to get through. So that's part of the challenge of learning calculus, all that notation, understanding exactly what it means, and learning how to use it. So that's one challenge. But okay, what are we studying? What is it? There's two general divisions, two general ideas. And for a long time, people thought they were both separate ideas. And again, this birth of calculus is when they realized that they were in fact connected to each other. So the first one is the idea of figuring out the instantaneous rate of change of a function. So for example, just as a general guideline, let's say that I have a function that maybe does that, right? So here's some function f of x. And let's say that means I have an input. I'm just making up some numbers. I'm just making up a function. Let's say that this value here, 3, goes up to there. And then over here, let's say that output is 8, right? So we would say that when the input is 3, the output is 8. So we can also rewrite that as f of 3 equals to 8, right? But also note that if we go over here, here's this other point, and so there's another value on the input. I should do some more labeling here. So let's say this is x over there, and so this is the outputs, which are f of x. Okay, but there's another point over here. Let's call it, I don't know, how about 5? So when we input a 3, we get an 8. When we input a 5, we also get an 8. So we would also write down that f of 5 equals to 8. Okay, but we would want some more information, right? Because note that here, when the input is 3, the output is 8, but then there's more information to be had because the graph is on its way up. We want to convey that information, that at this point, at this very point, the output is 8, but also that it's on its way up. Versus over here, at this point, the input is 5, but the graph, it's on its way down. It's decreasing, right? So that's where this idea of instantaneous rate of change comes in. What we want to do is we want to find the slope of the line that touches the graph at just that point. And I know that doesn't look like a straight line, but it's supposed to be a straight line. So the slope of this red one is going to be the instantaneous rate of change. It's going to tell us a little bit of information about that point, right? It's telling us that it's on its way up, right? The angle of that line, the slope of that red line will give us some information about not just the fact that the output is 8 at this input of x equals to 3, but also it's telling us that it's on its way up with the angle of this tangent line. Okay, and then over here, same thing, we're going to have another tangent line. Well, that was terrible. Ugly, but there it is, something like that. So then the slope of this one will tell us some information about that point. So we have more to go on. We know that when x equals to 3, the output is 8. And also at that point, because the slope is positive here, we know that it's also increasing. And then over here, we know that when the input is 5, the output is also 8. But now we have some more information. We know that the slope is decreasing. Okay, so we're going to, let's use technology to make this a little bit better. I can do a better job of explaining this using technology. So let me use this guy. So this is Desmos. It's a free online graphing tool. And so what I've done here is I've created this function. It's a parabola. It's a quadratic function. Okay, and so what I want to do is think about that tangent line, which I've already created here. I think it's this guy. So here's this. Across this, you see that tangent line right there. So for example, if we stop, let's label it. We stop somewhere around here. Let's see if I can nail it. Right there. So at this point, for example, we have that the input is 4, the output is 11. So we have the input is 4, the output's 11. But now we have some more information. We also have that the angle is positive of the tangent line, right? The slope of the tangent line is positive. So we have some more information at that point. The input is 4, the output is 11, and I know that it's growing. It's on its way up, right? The instantaneous rate of change is going to be positive at that point. Compared to, look at this, if we go all the way over here, we see that there's another place where the output is also going to be 11. When x equals to 6, the output is also 11, but now it's on its way down. Okay? All right, so I know that I'm going pretty fast at this point for some of you guys. That's okay. Don't worry about the technicalities of how we're going to do this. We're going to get to that as we move forward. I just wanted to give you an idea. Part of what we do is going to be to come up with a way to find the slope of that red line. Okay, the other thing that we do in calculus, the other part of calculus, which at first seemed like it was independent, but in fact turns out that it wasn't independent, that both of those are related, is the following idea, the idea that we want to find the area underneath a curvature. So if we have some function that does this, for example, here's some function. This is some f of x, and here is x, and here is some f of x. Okay, so we're going to have some input value here, and I'm just making up numbers. Let's say that is a 3, and that leads to 5. And let's say that over here, let's make this a 7, and let's say that leads to 8. Right? I'm just making up some numbers. Don't worry about those values for now. What we want to do is come up with the way to find the area underneath this curvature. Pretty ugly, but you get the point. So why do we want to do that? Well, math lives in an abstract world, right? It's just equations we create, and in that little abstract world, it might be hard to see why we care about anything. But not all of it, but a lot of math is useful because those equations in this abstract world can be translated to something in the real world. The abstract functions are representative of something in the real world. So this function here, this black curvature here, this curve, could represent something. Maybe it's the number of inches of rain. At 3 o'clock it was raining this much. At 7 o'clock it was raining this much. Perhaps it's the cost of something. Perhaps it's the quantity of units sold. Perhaps it's the number of internet visitors to some website. It could be all kinds of things, right? It could represent something in the real world. And so therefore, the area underneath the curvature could be used to represent something. So we work in this abstract world so that we can then translate it to something useful in the real world. And as it has turned out, calculus is very useful for lots of stuff in the real world. So that's why we care. So that's the other big part of calculus, finding areas underneath curvatures. At first it seems no big deal, right? We've been finding areas of shapes for many years. So you found the area of a rectangle, you know the area of a triangle, the area of a circle, you know all kinds of areas. But this is not quite that because of the curvature, right? If this was a straightforward rectangle, no problem. If this was a triangle, no problem. But it's not, that's none of those things. It's got a weird curvature to it, so we have to find a way to find that area. Okay, so that's the other big part of calculus. Two big parts: finding the area of underneath a curvature, and finding the instantaneous rate of change or the slope of a line tangent to a function at a point. Again, I can use Desmos to do a better job of explaining or demonstrating that. So here we have another parabola, and I can show that we might be interested in the area underneath between two values. I can move this guy here. So for example, it could be when, area between 1 and 5. So the area between 1 and 5 underneath this curvature, which is explained by this equation up here. But don't worry about the details right now. I'm just giving you a general outline, a general idea of what we're about to do in the coming chapters. So I hope I'm not overwhelming you too much with the details. Don't ignore all those details for now. It doesn't matter the actual equation and all that. I'm just letting you know we're going to be given some sort of equation, some sort of a function, and our goal is going to be to figure out a way to find the area underneath that function. So we're interested in figuring out the area underneath the curvature. That's one big part of math. That's the second part. I'm sorry, one big part of calculus. That's the second part of calculus. We'll focus on that down the road. But for now, we're going to spend a lot of time focusing on this first one, which is finding the slope of the line tangent to a function, right? The tangent meaning that it only touches it at one particular point. Okay, so how do we find the slope of a line? Well, we all remember, hopefully, from algebra, that if we have 2 points on the line, we can easily find that slope, right? We can use rise over run, the formula for slope, and find that slope. But the problem here is that there's only 1 point, and we don't have another point on the red line. We can't find the slope of the red line by simply using that formula because we only have 1 point, and we really don't have another way of finding another point on the red line. So what do? What we're going to do is, if we want to find this one, right, we want the slope of this red line, we're going to keep this one fixed, right? For the purposes of finding this tangent, the slope of this tangent, we're going to keep this one fixed. And then we're going to approximate it by finding another point or using another point. Like let's say we use this point right over here. It's on the curvature, right? It's still on the curvature, like this. And it's kind of close to the blue one. So we're going to keep the blue one fixed. We're going to get another point. And then we're going to draw the line that connects those two. So here it is, like that. So now the green line, we can find the slope of that green one because there's 2 points. There's this point and there's this point. And in fact, let's label it. There it is. So here are the coordinates of this black point. We have the coordinates of the blue point. We can use rise over run and come up with the slope that connects them, right? Okay, and again, this is just an introduction, so don't worry too much about the formulas. We're going to get to that, and I'm going to spend a lot more time on that when we get to it. I'm just giving you an idea of what we're going to do in the coming sections. Okay, so what we want to do is go, okay, well, this is an approximation of the slope of the red line by finding the slope of the green one. But you can see right away that it's not a very good approximation at all. It's kind of off, right? So how do we get it to be a better approximation? What we're going to do is we're going to get this a little bit closer, right? As the black dot gets closer and closer and closer to the blue dot, we see that the slope of the green one is going to get closer and closer to the slope of the red one. And once we set up a formula that helps us do that in general, then we're going to be able to use the idea of letting the black dot get infinitely close to the blue dot. And at that point, we would say that we found the slope of the red one. That's what we're going at, right? So we're going to get infinitely close, and then at that point we'll say, okay, well, we found it. All right. For that reason, studying calculus is a lot about studying infinity. What happens as 2 points get infinitely close to each other? What happens when one point goes off toward positive or negative infinity, right? So that's a lot of what we're going to be doing. For that reason, this course begins by studying limits. Limits is about that very situation. What happens when things get infinitely close to each other? So it seems a little bit disjoint when we get started. People don't quite understand why limits are important or how they relate to what we're doing. So hopefully this has given you some idea of what we're doing in general, right? Just a quick, simple little overview. Don't worry about the actual numbers and the actual equations. Hopefully I haven't overwhelmed you too much. I just wanted to give you a sense of what it is we're going to be doing this semester. Okay, so we're going to spend the whole semester thinking about these two ideas that I just explained. But for now, we're going to slow it back down, go back down to basics, and introduce this idea of limits. When 2 points get infinitely close to each other, we're going to develop some notation and get comfortable with like the really, really, really simple cases, so that when we build it up to something more complicated, we're ready to handle it, ready to deal with it. All right, so let's get started with limits. All right, Chapter 2, Section 1, Introduction to Limits. So a couple of key concepts. In this section, or in this chapter, we're going to introduce the derivative and define what that means, work with it. In a later chapter, we're going to introduce integrals, right? So derivatives are more closely associated with that first issue about finding the slope of the line tangent to a point, and integrals are about finding the area underneath a curvature. So those are the two main big concepts that we work on in this class. Okay, first let's start off with a brief review of functions. So let's say that we have this equation, f of x equals to 2x minus 1. Simple, straightforward, linear equation. We know a lot about this kind of an equation, I hope. So we know that when we're dealing with an equation like this one, this is indicating that f of x equals to 2x minus 1. We know that we can also go back to the other style of notation, y equals to 2x minus 1, where we know that that would mean that x represents the inputs or the domain, and y represents the outputs or the range. Good. Because this is a linear equation, we know that 2 is the slope, and we know that minus 1 helps us identify the y-intercept. So we have a y-intercept point at 0, negative 1. Okay, so we know a lot about this line. So we can use this there's different ways to express ordered pairs using this notation. So we can use x, f of x, right, to represent a point. So for example, when x is equal to 2, then we can write f of 2 equals to 3, right? How do we get that? Well, we get that through the following. F of 2 equals to 2 blank minus 1. Well, I shouldn't. So this, f of x equals to 2x minus 1, that's this, right? The input goes right in here. Let's put it in green. The input goes right in there, which means that we also put the input right in there. So in the case of x equals to 2, we would put a 2 right in there and a 2 right in there, and then calculate this. And so we end up with f of 2 is going to be equal to 4 minus 1, which is equal to 3. When the input is a 2, then the output is a 3, right? And we can express that in a variety of ways. We can say that 2 comma f of 2, we can say 2 comma 3 as the ordered pairs that are solutions to this one solution of this equation, right? All right, let's do a couple more. So for instance, if x equals to 0, then again, following this little pattern over here, we have that f so when x is equal to 0, put a 0 there, put a 0 there, and so we end up with f of 0 equals to 0 minus 1, or just negative 1. So we have a variety of ways in which we can express this. We could say, of course, that when the input is 0, then the output is negative 1. We can just write it like that. Or we can also write 0 comma f of 0, where, of course, we know that f of 0 is negative 1. Good. So just pointing out there's a couple of ways that we could do that. Okay. Likewise, when x is equal to negative 1, we have f of blank equals to 2 times blank minus 1. And so x equals to negative 1 means we put a negative 1 there, put a negative 1 there. And then simplify this. We get 2 times negative 1 is negative 2 minus 2 is negative 3. So we get negative 3. F of negative 1 equals negative 3. So again, we could just write the ordered pair negative 1 comma negative 3. Like that. Or we can write negative 1 comma f of negative 3. Oops. F of negative 1. Sorry. Where we have to know that f of negative 1 is negative 3. Okay. All right. Well, what we have found here is a couple of values in the domain and a couple of values in the range, right? So we can also begin to put that together and say the domain, I would say 0, comma, negative 1, and 2 are elements of, members of, this little e here is elements of the domain. And also we have found a couple of values that are in the range. We also know that, for instance, negative 1 is in the range because of here, right? The output was negative 1, so that means that the output is in the range. This negative 1 comes from the fact that this input was negative 1. Another one we found was this 3. And another one we found was this negative 3. So negative 3, negative 1, and positive 3 are members of the range. Good. Let me highlight them. So the domain values were when x equals to 2, we got a valid answer. When x equals to 0, when x equals to negative 1. So 0, negative 1, and 2 are members of the domain. On the other hand, once we inputted a 2, one of the outputs we got was this 3. Another one of the outputs we got was this negative 1, and another one of the outputs we got was this negative 3. So we have found that negative 3, negative 1, and positive 3 are members of the range. We have not found the complete set of the domain yet because I just kind of randomly picked some values in the domain and some values in the range. Okay, just getting used to the language. So what is the entirety of the domain? I just found 3 members that are part of the domain, but what's the entire domain and what's the entire range? Well, to find those, we can do it in a couple of ways. One thing we could do is graph this. Since it's a linear equation, we should be really comfortable with graphing linear equations. So it's 2x minus 1 we have f of x equals to 2x minus 1. We know that the slope is 2. The y-intercept is negative 1. So we know that it should look like this. Here's f of x. And I'm going to draw it in blue. So I know it goes through the point 0, comma, negative 1. 0, comma, negative 1, like that. Just drawing a sketch here. So this is the point 0, comma, negative 1, which is the y-intercept. And I know that the slope is 2, so I can retrace my little triangle steps here, right? The slope equals 2. Usually we use the letter m to represent slope. And we know that slope, m, is equal to rise over run. Right? So what we can do is we can take this 2 and put a 1 underneath it. We've converted it into a fraction. So therefore we know that this is the rise and this is the run. So I can use that information to kind of recreate a little triangle here. And so it would look something like that. And it's kind of ugly looking here. I don't know if it looks accurate here, but the run is 1, the rise is 2. So this is saying that this here is a 2, and this is a 1. Rise over run. Rise over run. Good. So we get to another point. If this was at 0, negative 1, and we go 1 unit this way, that means that this is going to be a 1 here. Right? We go 1 unit this way. From 0, we go across 1 unit. And then starting at a negative 1, we go up 2 units, so we get to positive 1. So there, we get 2 points. There they are. We can connect those 2 points, and there's our line. Kind of messy, kind of ugly. Hopefully you get the point. But we can do an even better job with Desmos. So let me do Desmos. So Desmos.com if you want to use it. Free graphing calculator. And then I can just graph f of x equals 2x minus 1. And let's put it in blue as well. So here it is. And there's that line. And from here, what hopefully you can notice is that the domain is going to be all the possible values we can input, and the range is all the possible outputs that we get out of it. And so for a linear equation, the domain is all real numbers, and the range is also all real numbers, right? No matter how much I zoom out, the line just keeps going that way. So the domain is all real numbers. The domain is all the values down here, all the values of x, right? So this is all the input values of x. Any number in here has an output, so it's a member of a domain. And then all the values over here, let's put it in green, all of these values are members of the range. In a more general setting, let's say we have x and f of x over here. If we have some function, let's say the function does this, like that, from there to there. So this is our function f of x. And let's say that this first value right in here is the number 5, right? It's just an arbitrary selection. It doesn't matter. Nothing special about 5. And this output value, this other value over here, let's say it's the number 13, right? And then this one translates there to the number 4. And then this guy over here translates to the number 17. Something like that. Okay, so then what we're going to say is that this represents the range. The values between 4 and 17, all the values between 4 and 17 are possible output, and the domain is all of these values. Domain is all of this over here, and the range is all of this over here. All possible outputs are the range. All possible inputs are the domain. Okay, well, in a more general setting, there was no special reason for why I chose a 5 or a 13 or a 4 or a 17. So let's just erase those and put it in a more arbitrary setting and say that it's good old-fashioned letters. Let's go from A to B. The domain is going from A to B, and the range goes from C to D. Right? So then we would say the domain of this function is equal to, and I did put closed circles, so let's be inclusive. It would be from A to B inclusive, and the range would then be the values from C to D, again inclusive because they have closed circles on there. Okay, so let's get back to this. Okay, so here's another graph of the exact same thing. We have our equation. This blue line is f of x equals to 2x minus 1. And then we have a couple of ordered pairs that are on that line. We have x equals to 2. When x equals to 2, we get an output of 4. So we get the ordered pair 2, 4. And we also have the ordered pair 2, f of 2. Right? So it's important to get used to that style of notation. Over here, we have another point, this point right over here, on the line as well. That point is achieved when x is equal to 0. When x is equal to 0, we get an output of -1. So we get that ordered pair right over there. And so again, we can write it down in the same way. That point right there, let's put it in green. That point right there could be identified as the point 0, -1. When x is 0, y is -1. Or it could also be referred to as 0, f of 0, right? The output of the function when the input is 0, which we know is going to be -1. Right? Same thing over here. This point right over there is the ordered pair -1, -3. Or we can refer to it as -1, f of -1. All right, just getting used to notation. Finding functions values from its graph. Okay, so complete this table. All right, so now we have a graph. They didn't give us the actual equation. There's different ways in which functions can be represented, right? We can have an equation, which is the most common thing we work with, 2x minus 1, 5x squared, an equation. We can also have a graph, just a picture given to us. This blue line represents a relationship between the inputs and the outputs. We can identify a particular input in the x-axis and then trace it up or down to the blue line and find its corresponding output value. We can also express functions by a verbal description, right? Literally writing double the input, subtract 7, 2 less than double the input. You can verbally describe it. So we're going to work with a variety of ways to express functions. And so if a graph is given, like this, no equation, then we can find these values by simply interpreting it from our graph. When the input is -1, right, we got to come over here and find it. So let's use a highlighter. Here's -1. When the input is -1, we're going to retrace this. So we're going to go up or down to find the blue line. So in this case, we're going to go up, and we go right over there. We find it. And then that translates to a 5. Let's see if I can zoom in a little more. And then that translates to a 5. So just by reading this graph, I could see that -1 corresponds to a +5. Good. And then 0, here is x equals to 0 is right here. And I can see that it translates up to a +2. So I can get that as a 2. And then when x is 1, here's 1, this is a case where I have to come down. And looks like 1 translates to a -1. Notice that when we are interpreting graphs this way, we might not get the exact answer. because, I look at this and I go, okay, yeah, it looks like -1. Someone else might look at it and determine it's -0.99, right? It's an interpretation that we have to make. So we do sacrifice accuracy when we are just working with a graph like this. But there are some values, some benefits to working with just the graph instead of an equation. And in this case, what we're doing is we're going to introduce the idea of limits, and we're going to begin with graphs because it's easier to see it before you work with the equation. Okay, so now the last one, when x is equal to 2, here's 2, x equals 2, and then we trace it down, and it looks like it's going to be about there, about a -4. So we can fill out the table this way. Okay, so analyzing a limit. So the limit of a function at some point x equals to a involves examining the behavior of the output values of the function as the input values get increasingly closer to the value a, right? So that's what we're going to do. What does that mean? So just roughly here, let's say we have a function. So we have x here, we have some f of x over there, we have some function that will, I don't know, look like that. And say we're interested at a. So let's say here is a, and it leads to that point right there. We want to figure out what happens as values get closer and closer to a. So we don't really care about the actual value when the function equals to a. Let's say a, just to pick a random number, let's say a leads to 9. Let's say a leads to 7, right? What we want to do is think about what happens as x values get closer and closer to a, as we let x equal this point here on the graph. Okay, that traces to that, and we get some. Okay, but that's not good enough. How about if we get closer? What if x is this point? Let's subscript them as x sub 1, x sub 2, x sub 3. And we want to approach it from both sides, x sub 4, x sub 5. As we get closer and closer and closer to the value a, we're going to be examining all these outputs from those values and start to get a sense of where the function is going so we can find what we call the limit, right? The limit of the function as x approaches to a. Okay, this is a little arbitrary. Let's get back to our equation that we had before. Let's say we had the equation that we had before. We had the equation, this was the equation 2x minus 1. F of x equals to 2x minus 1. For example, when x equals to 2, we saw that we plug in a 2 in there, we get a 4 minus 1, we get a 3. Right, so f of 2 equals to 3, right, there it is, 3. And so we can write down the ordered pair 2 comma f of 2, or we could say that that's equal to 2 comma 3. Right, all those things mean that. Okay, but what if we wanted to find the limit as x approaches 2? So not exactly equal to 2, but as it gets closer and closer to 2. So we're going to let one of those x values be this point right here, for example. Let's call that x sub 1. We're going to analyze our equation, get an output, and see what happens when x at x sub 1. But that's not close enough, right? So we want to get closer. How about if we let the next x value be a little closer? That's going to be x sub 2. Maybe x sub 2 is 2.9, for example. Still not very close. We want to go from either side, so maybe the next one we try is maybe this one. X sub 3, that's going to be maybe 1.4. And get even closer, right? So the point is we get closer and closer and closer to x equals to 2 from both sides, and we keep analyzing what happens to the output values, and hopefully we start to see a pattern. From that pattern, we'll be able to determine the limit as x approaches to 2 for this particular function. Let's organize all that with a table, and in order to be able to do that, we're going to incorporate a calculator. But before we do that, let's just do it for some really, really simple ones, just following the simple equation and following the graph. we want to do this. So here is like a table of values. Here's f of x. Oops. Here's x, the inputs, and f of x. So we want to figure out the limit as x approaches to 2. So here's the target 2. And, well, the fact is we don't really care what it equals at 2. We want to see what happens as we get closer to 2, right? So let's leave that blank for now. And what we want to do is approach it from either side. So we're going to maybe plug in a 1. Let's say we plug in a 1 from there. Well, let's start off with 0. If we plug in a 0, we know we're going to get a negative 1, right, from here. Let's write down the equation up here. This is 2x minus 1. So if we let x equal to 0, we get a negative 1. If we let x equal to positive 1, we get a positive 1. And then we want to get closer. So what we want to do is figure out what happens when we plug in a 1.1, about a 1.7, about a 1.9, about a 1.99. Right? We want to get closer and closer and closer and closer to 2 without ever actually equaling the 2. And we want to approach it from the other direction as well. So we want to start off at, say, 3, and then go, okay, well, that's not that close. How about 2.9? How about 2.7? How about 2.2? How about 2.1? How about 2.01? Right? We want to get closer and closer and closer to 2 from both directions. And we want to establish, hopefully, that there's going to be a pattern that begins to emerge for the outputs, that the outputs begin to approach somewhere. And it's that approach that will let us know what the limit of the function is as x approaches to 2. Now, to calculate all these outputs here, all these values, that would be a lot of arithmetic, right? So, for example, to calculate this 1.9, we need to calculate this. We need to plug in a 1.9 into this equation. Okay, it's not terrible, but it's a little bit of work. And then once we're done with that one, well, we need to figure out what is 1.99. Then we need to figure out what is 1.99. And then after that, it'll be 1.9999. And then after that, it'll be 1.9999999. So you can see that the arithmetic is going to get kind of ugly. So we need technology to help us do that arithmetic, right? So for that purpose, let's start using our calculator. Let's pull out our calculator and learn a way that we can fill out this table in a nice, easy way. Okay, so turn on your calculator. You might find yourself in a weird screen you've never used before if you've never used this before. So hit quit. So this is an ancient technology before iPads where we had buttons. And so in order to make the button do different things, they wrote in different colors around the button, on the button, above the button. And what we want to do is select the color in order to match what you want to do. So if you just click this button, it might do mode, it might react the way it reacts under mode, or it might do this, and that's what we want. So we want to hit second and quit is what we want to do. For example, continuing on that, say the button 5. The button 5 does 3 different things. It could be a 5, it could be an L sub 5, or it could be a U. If I want it to be a U, I want to hit the green button first. Notice that that blinking cursor turns into a blinking A to let you know that the alpha lock is on. And then when I click 5, it's not going to do 5, it's going to do a U. Okay? And if I want it to be L sub 5 instead of just 5, then I first want to hit this second, right? So now you see that the little blinking guy is an up arrow. That lets you know that this second button is active, which means that when I hit the 5, it's not going to be 5, it's going to be L sub 5. Good? And if I don't hit either one of those, you just have the blinking box, then when I hit this, it's just going to be a 5. Okay? So that's how we can select different things. So if you find yourself in an unusual screen when you first turn it on, hit second, quit. That'll do this. So it'll get out of those screens, take you to your main screen. There might be a bunch of writing on there. It remembers what the previous equations were. So hit clear, and it'll hopefully clear your screen for you. Okay, the first thing I'd want you to do is go over to where it says mode. So now let's hit mode. And make sure that your calculator has these settings so that it's under normal. This is under float, radians, functions, right? So some of these things are important, some of them are not so important. How do you change it? Well, if you use your arrows, you can go to a different thing. So like, let's say I choose this 3. If I want to select it, I hit enter. And now instead of float, it'll say 3. But we don't want that. We want float. So go over here and use your arrows and select float. Okay, good. So we want these settings here. Now, when you're done with that, then hit quit again. You're back to your main screen. Okay, we're going to go over to where it says y equals. Hit y equals. Here's where we're going to input equations. And there might already be equations like there's one here. So if you don't want it, let's hit clear to get rid of it. So go down and clear all of them, get rid of them, start from a clean slate. Okay. Next, I want these plot things here, I want them to be deactivated for now. We're not going to use them right now. And how do you know they're active versus inactive? Well, if they're dark like this one, it means it's active, it's on. And in plot 2 and plot 3 are off because they're not dark like that one. Okay, so go up, use your arrows, highlight it, and then hit enter. When you hit enter, it'll toggle between on and off, right? It's the on and off button. So on, off, on, off. So see, I turned 1 off, but turned 2 on. So I don't want any of them on right now. We'll deal with those later. Make sure all those guys are off. Okay, this is where we're going to plug in our equation. That first equation we're dealing with is just 2x. Now the x is this button. It has a variety of variables on there. But depending on the setting that you're in, your calculator will know which one is the one you need. If you click on here, it should print an X. If it does one of the other ones, the theta or the n or something, it means that you didn't do that mode step. So if you're not getting that, go back to mode and make sure that you have it under the settings I put. Particularly function is what it needs to be under. Okay, so it was 2x minus 1. Now remember that in our calculator, this little symbol means 2 different things. This is subtraction, and this indicates that it's a negative, and we can't interchange them. So we want subtraction 1, not negative 1, right? It wouldn't make sense to have 2x negative 1. It's 2x minus 1. Okay, so we have our equation there. The next thing we want to do is go up to where it says table set, right above Windows. So we're going to hit second, and then table set, right above Windows. And then here, we're going to make sure that the independent variable is under ask, and that the dependent variable is under auto. These things don't really matter. So go down, use your arrows, and change it. So if yours is like this, as many of them are, make sure you use your arrows, select ask, and hit enter, like that. So once those are like that, we're going to go over where it says table, again in blue. So we want to make sure we have that second button active, and then we're going to hit table, and we get to this. Okay. Once you get to this, let's just begin by deleting the old ones. So hit delete, 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 erase all of them, make sure that we start with a clean slate. Now, what is this? What this is a place where you can evaluate your equation, y sub 1. Notice that y sub 1 is this equation over here, y sub 1. We put in 2x minus 1. So now that we've gone through this process, here I can just input the number, like let's say I put in a 0, and we know that the output better be a negative 1. We already got that from before. 0 leads to negative 1. And we can also just plug in other numbers here. Like let's say we put a 2, and it's going to evaluate that function at 2 and get me to 3. So this is a really good, easy way for me to get input, output values from my equation. Okay, so let's go back to the few values we already have for the equation 2x. For the equation 2x minus 1, right? That's the same equation that we plugged into here. That's the same equation we plugged into here, 2x minus 1. And so we can go to table, And we have that when x equals to 0, the output is -1. When x equals to 2, the output is +3. So we get that 3 from there. And so now we can type in values for the input that are closer and closer to 2 from either side. So let's approach it from the left-hand side first. So let's say that we wanted to get closer to 2. So how about 1? That's good, but we can get closer. How about 1.5? About 1.7? How about 1.9? About 1.99? About 1.999, 3 nines, about 1.9999. Okay, so we can see the pattern that happens. As the input values get closer and closer and closer to 2, but never actually 2, the output values are getting closer and closer and closer to 3, but not actually 3, right? What about the other direction? You see that the other direction, we get the same thing. So let's say we start off at something like a 3. Let me come back up here. Start off with like a 3. And then we get a little closer to 2. How about a 2.7? About a 2.5? About a 2.2? About a 2.1? About a 2.01, about a 2.001, about a 2, how about a 2.123 zeros and 1. Okay, so we get closer and closer and closer to 2 from the right-hand side of 2 on the number line, and we see that we get closer and closer and closer to 3, but not exactly 3. So that's what we want to think about when we think about the limit as x approaches to 2. What is happening to the output values? What are they approaching? And we can organize all of this into a table now. So that's what this represents. Something like this. Notice that we have our input values, and they're getting closer and closer to 2 from the left-hand side, closer and closer to 2 from the right-hand side, and the output values are getting closer and closer and closer to 3 from both directions. So we express all that using the following notation. This, the limit as x approaches to 2 of the function f of x equals to 3, where the function f of x is described as 2x minus 1, right? So this is the notation we want to introduce, this symbol right here that represents the limit as x approaches to 2. Okay. Here's another example. Let f of x equal to x plus 2. Discuss the behavior of the value of f of x when x is close to 2. Okay, so again, we care about the value as it gets closer and closer to 2, not the actual value of the function at 2. So there's the actual value of the function at 2. We know that if we plug in a 2, we get a 4. So we know that 2 comma 4 is this point right there. But what we care about is what happens to this function as we get closer and closer to 2 from either direction, right? The limit as x approaches to 2 from either direction. Well, we can see in this picture, we can see by the picture that the outputs are going to get closer and closer to 4 as we approach 2 from either direction. So, for example, if we have this little value right here as x sub 1, it's going to result in that output. And if we let x sub 2 be a value over here, then it's going to result in a value over there somewhere. And then x sub 3 could be a little closer, like that one. Could be a point there. And then x sub 4 could be a value there, gets a little closer and closer and closer until we reach our limit. Okay, so that's described this way. As the inputs get closer and closer to 2 from both directions, we trace them up to the graph and we see that the outputs are going to get closer and closer and closer and closer to 4. Okay, so we would say that the limit as x approaches to 2 of our function f of x equals to 4. Right? This equation reads the limit of f of x as x approaches 2 is 4. In this example, the value of the function at 2 and the limit of the function as x approaches 2 are the same. But that doesn't always have to be the case, right? So it's the answer to the limit, right? The limit as x approaches 2 of f of x equals to 4 is independent of what the actual value of the function is at 2. I mean, they won't always be the same. Okay, definition. We write that the limit as x approaches to c of f of x equals to L, or another way of describing that is that the function f of x approaches L as x approaches c if the functional value of f of x is close to the single real value L whenever x is close to but not equal to c. Right? What in the world is all that? Let's just do a quick little sketch to describe what this is saying. So let's say we have our function f of x. Here's x, some f of x value. So let's put it in blue. Let's say that this function does that kind of a thing. We want to say that here is a point, and we're going to say that that point is c. So this is the point c, right? This is the point x equals to c. And we want to say that this is some value L over here. So as x approaches to c, as the input values are chosen, closer and closer and closer and closer, as we get closer and closer and closer to c from both directions, we see that the resulting outputs, right? So this resulting output was right there, and then this resulting output was right over there, right? As the various values of the input values x get closer and closer to c, the resulting output values get closer and closer and closer to L, right? So we can describe that in either this way. We can say the limit as x approaches to c of the function f of x. So this is the function f of x here, is equal to L. Or the other way we can express this is by saying that f of x approaches L, the function approaches L as x approaches to c. So some people prefer this way of describing it. Some people prefer this way. I think we're mostly going to be sticking to this style of notation, but this is perfectly good as well, right? Whichever one makes most sense to you. And again, notice that this is independent of what the actual value of the value c is. For example, there could be a hole there at c, meaning that the function is not defined at c. That's possible. Or it could be that the function is in fact defined. Maybe it's a solid dot right there. So maybe the actual value of the function when x equals to c might be this one, right? This might be the ordered pair c comma f of c. But the limit stays the same. The limit doesn't care about what the actual value at x equals to c is. The limit cares about where is it going, right? It's about what it looks like. It looks like it's heading right here. That's what it looks like. We don't really care what it is. We care what it looks like. Like many things in life, I guess. We care about what it looks like, not what it actually is. Okay, so note that the existence of the limit as c is independent of the value of the function at c. In fact, c may not even be on the domain of f. However, the function must be defined on both sides of c. That's what we care about. All right, moving on. Here's another example. The absolute value of the function is defined this way. F of x equals to the absolute value of x. What does that really mean? Well, here is one way to describe what that means. It means that it equals to x if x is positive, greater than or equal to 0. And it means that it's equal to -1 times x if x is a negative number, less than 0. Right? This is instructions on how to deal with this absolute value. Right? In other words, if we have this absolute value like that, what's the answer? Well, it kind of depends on what you input is. So if we input a 3, and we go, okay, well, it's a 3, well, then the output is just going to be 3. Leave it alone, right? If it's a positive number, we just leave it alone. Whatever the input is, just repeat it. Ignore the absolute values. That's the same answer. On the other hand, if we input a negative number, like let's say we input a negative 5, then we input a negative 5, we end up with a negative 5 here, and now the answer is going to be negative 5 times negative 1, right? We need to multiply it by that extra minus to guarantee that we end up with a positive 5, right? So if we input a positive, leave it alone. That's what this is saying. If we input a positive number into our function, then leave it alone. That is your answer. 0 or positive, strictly greater than or equal to 0. On the other hand, if we input a negative number, if what you're inputting is negative, then multiply that negative times negative 1, thereby making it positive, right? So notice that this minus sign here, this one, that's this right here. So if the input is negative, multiplied by an extra negative 1, thereby making it positive. Okay, so that's one description of absolute values and how to deal with them. All right, now let's take a look at the graph of the absolute value of x. So if we go back to Desmos, f of x equals 2. Let me use this guy over here. Absolute value of x. Like this. Okay, so here's what the graph of the absolute value of x looks like. Notice that when x is a positive number, like 5, then the output is 5. When you plug in 5 into the absolute value function, you get a 5 out. When you plug in a negative 5 into the absolute value function, you get a positive 5. So if you input a positive number, you get the exact same positive number. If you input a negative number, you get the exact opposite number. You multiply that number by negative 1. Let's graph the point. So slider go away, and then I want to graph the point. So for instance, if we plug in a 1 into our function, the output is going to be 1, right? For any one of these positive numbers, we plug in that positive number, the output is going to be that same positive number. But if we go over here, then if we plug in a negative 6.7, then the output of the absolute value function is going to be a positive 6.7. So it's got this V shape, right? The graph of the absolute value of x is got this V shape. The equation for this part of the graph is really just equal to y equals to x, whereas this one over here, just this part of it is y equals to negative x. So let's explore what happens if we have this function. Let h of x equal to the absolute value of x divided by x. Explore the behavior of h of x near but not equal to 0. Find h of x if it exists. All right, so let's begin by creating a table. So if we create a table of values, we have x here, we have h of x. We can try a couple of values, like let's say we try 3. What the heck just happened? Like let's say we try 3. Then that means we want to find h of 3. H of 3. H of 3 is going to be equal to the absolute value of 3 over 3. And as we saw before, if we plug in a positive number, then the output is just that exact number. So we just get a 3. 3 over 3. Oh, well, that's just going to be a 1. Okay, we care about what happens near 0, right? Okay, so we got to get closer and closer to 0. How about 2? That would be h of 2 equals to the absolute value of 2 over 2. Well, that's just going to be 2 over 2. That's just going to be 1 again. Okay, how about 1? H of 1 equals to the absolute value of 1 divided by 1. Well, that's just going to be 1 over 1, which is 1 again. Starting to see a pattern. Okay, how about in the other direction? Skip on over to the other side. Right. Ultimately, I want to get to 0. So I'm just going to skip on over to the other side, and then I'll zoom out in a second, and we'll see the whole thing. So let's say from the other side I want to approach this. So let me jump over to like -3. H of negative 3, which would be equal to the absolute value of -3 over -3, right? The input is -3. And we know that when we deal with absolute values, we are instructed that that means that if we input a negative number, we have to multiply the input by this extra -1. Okay, so we end up with -1 times -3. That's how we deal with the absolute values, divided by -3. So we'll end up with a positive in the numerator, +3 over -3, which gives me -1. Okay, so remember, we want to get closer and closer to 0. So how about -2? H of -2 is going to be equal to the absolute value of -2 divided by -2, which then again will be -1 times -2 divided by -2, which then gives you +2 over -2, which gives you -1 again. All right, again, we're going to get closer and closer to 0. How about -1? That would be h of -1. Well, that's going to be the absolute value of -1 divided by -1. We already know this trick by now. It's going to be equal to -1 times -1 divided by -1, which equals to 1 over -1, which equals to -1. Okay, but we want to get closer and closer to 0. So we want to figure out what happens as we get closer. How about -0.5? How about -0.1? How about -0.01? -0.001? That's what we want to know, right? We want to know those things. And then the same thing from the other direction. As we get closer and closer to 0 from the other direction, I want to know what happens when the input is +0.5, when it's +0.2, when it's +0.1, 0.01, 0.001, right? That's what we want to know and figure out the outputs. And from those outputs, I want to get a sense of what's happening with this function. So, for example, if we tried 0.2 or 0.5, so if we go back to this, we see from our pattern, let me zoom out, we see from our pattern that we always get a +1 as an answer whenever we input positives, right? Because in the numerator, if we input a positive number, then nothing changes. We get that same result. Absolute value of 3 is 3. Absolute value of 2 is 2. Absolute value of 1 is 1. Absolute value of 0.5 is going to be 0.5. Absolute value of 0.001 is going to be 0.001. Nothing changes. The denominator is the exact same value, so we're always going to get a +1 from this direction. Hopefully that's clear enough, that the outputs are always going to be 1 as long as the inputs are positives. Good. And then from the other direction, when we put in a -3, the absolute value of -3 is +3, and then the denominator was -3, so we divide them and end up getting a -1. And that's always going to be the case when we input a negative number. The numerator, we're going to strip away the negative. The denominator keeps its negative, and so the division is always going to be -1. So as we approach 0 from the other direction, we're always going to end up with -1s. Okay, so as we approach 0 from the positive sides, 3, 2, 1, 0.5, 0.1, as we get closer and closer to 0 from that direction, we see that the function is going to approach 1. And as we approach from the other direction, as we get closer and closer and closer to 0 from the negative side, we see that the outputs are always -1. If we graph this function, we see that it looks something like this. It's going to be a 1 whenever x whenever x is positive, and it's going to be equal to -1. It's going to be a 1 for any values that are greater than 0, and it's going to be a -1 for any values that are less than 0. But what happens at 0? So note that f of 0, we end up with an absolute value of 0 divided by 0, which gives me 0 over 0, which is an undefined. Okay, so what we can conclude from here is that the function, being both blue ones, they don't approach the same thing as x approaches 0. Right? As we choose values of x that get closer, and closer and closer to 0 from both sides, they don't agree. From this direction, they always approach -1. Right? The outputs approach -1. From this direction, the outputs always approach +1. They don't equal each other, so we'd say that the limit does not exist in this case. However, we do now open the possibility of the limit existing in one direction. So if we only focus on x approaching from the right-hand side, right, the limit as x approaches to 0 from the right-hand side, it always gives you the same value of 1. And the limit as x approaches 0 from the left-hand side, we're going to call this side the left, and this the right. As x approaches to 0 from the right-hand side, the limit equals 1. As x approaches 0 from the left-hand side equals to -1. So we open up the possibility of not having a limit because they don't match, but at least if we only focus on one side, one-sided limits, then they might exist. So let's define that, and I'll come back and write down these in a better way. Okay, definitions of one-sided limits. So we write that the limit as x approaches to c, and then this little minus, this tiny little minus there, means from the left-hand side, of f of x equals to capital K, and call K the limit from the left side of f of x. We write that the limit, and call K the limit of f of x, is close to K whenever x is close to, but to the left of c on the real number line. Okay, in other words, f of x, here's f of c. Let's say we have some function, and let's say that the function looks like this, and it approaches. So here is c, and from the left-hand side, it looks like as x gets closer and closer and closer to c, the outputs are going to get closer and closer to this value. So we're saying, let's say that value is k. So we would say that the limit as x approaches c from the left-hand side, top right-hand side of the letter c, that means that it's from the left-hand side. Again, notation is an issue with calculus, right? So why did they decide to do it that way? I'm not sure. It might have been nice if we wrote out the word left, for example, or put a little L there for left, but then, that causes other confusion. So it's just the notation we've decided on. So the limit as x approaches c from the left-hand side of our function f of x is equal to k in this case, right? So I'm drawing an example of what the graph would look like to satisfy this right here. As x approaches c from the left-hand side, only from the left-hand side, so we're restricting it to a one-sided limit, then the function output, the blue is the function f of x, its output gets closer to capital K. This one, on the other hand, is saying, oh, that's ugly that they use the same K here, huh? Right, of C. Okay, so now let's say that there is some other capital Q over here, Q, and that the function, again, the function is in blue, so let's say the function looks like this. And then maybe there is, in fact, another point right in there. And let's call that one. Okay, so from here I can see that the blue is the function, f of x. So from here I can get that f of the limit as, let's do the limit, the limit as x approaches c from the right-hand side only. That little plus sign there indicates that we're approaching it from the right-hand side now. So I'm choosing x values in my domain that get closer and closer and closer and closer to c from the right hand only, right? We're restricting our approach towards c with this little notation of my function f of x. And from the picture, I can tell that it's approaching capital Q. So this is a one-sided limit. The limit as x approaches c from the right-hand side of f of x equals to q. The limit as x approaches c from the left-hand side of f of x equals to k. So the one-sided limits exist. The left side limit exists and it equals to k. The right side limit exists, it's equal to q. But if I just openly say, does the limit exist at as x approaches to c, then the answer is no, because there must be a specific path toward approaching c. It only exists as long as you approach c strictly from the right side of c or strictly from the left side of c. But if you don't put that condition in there, then it doesn't exist because they don't equal each other. Okay, so if they don't put a little restriction, that little minus sign or a little plus sign, then by default they just mean it's unrestricted. You're allowed to approach c in any direction, and we can see from this picture that the limit does not exist in a case like that, right? So the limit as x approaches to c, no restriction, of f of x is, well, it doesn't exist. It does not exist in this case, right? The way I drew it. Because why? From the left-hand side it equals to k, from the right-hand side it equals to q. They don't equal each other, therefore the limit as x approaches to c does not exist. Now if we do a restriction and focus on just from the left-hand side, the limit as x approaches to c from the left-hand side, then it does approach capital K. And the limit as x approaches to c for just the right-hand side does exist, it approaches q. And notice that in the way I drew it, the actual value at x equals to c of f of x is equal to m. So note that in this, the way I drew it, f of c equals to m, which is neither k or q. So it doesn't really matter what the value of the function is at that point. What we care about is what happens as we approach it. Okay, moving on then. So for a two-sided limit to exist, the limit from the left-hand side, from the left and from the right limit must exist and must be equal to each other. So that is that the limit as x approaches to c of f of x equals to L, if and only if it's true that the limit as x approaches to c from the left-hand side of f of x equals to the limit as x approaches to c from the right-hand side of f of x. They equal each other and they equal to L. They equal to both sides. Right? So what was that whole thing? Notice that there's a little minus sign here, right? So this is indicating the left side limit. The left side limit. And this one over here, notice there's a tiny little plus sign right in there. It's indicating that this is the right side limit. So if the left limit exists and it equals to capital L, and the right-hand side limit exists and it also equals to capital L, they both equal each other, then we can just throw out the blanket statement that the two-sided unrestricted limit does exist, the limit as x approaches to c of f of x, and that limit equals to capital L, right? They both sides go in the same place. They go in the same direction. For the example we were looking up above, we had the case where we had our function was equal to f of x was equal to the absolute value of x over x. And we saw that as x approached 0 from one direction, we were always getting -1. And as we approached it from the other direction, we were always getting +1. Right? So the graph from above was roughly something like this. right? So as x approached 0 from the right-hand side, we were always getting an answer of positive 1. And as x approached 0 from the left-hand side, we plugged in negative numbers, we would always get negative 1 as our answer. So this is what we show to indicate the left-hand limit. Right? This little minus right in there, this is the left limit. So as this is the left limit, the limit as x approaches to 0 from the left-hand side of our function f of x is equal to negative 1. And then this is our right limit. Notice that there's this tiny little plus sign right there. That little plus sign there shows that we're approaching 0 from the right-hand side. The limit as x approaches to 0 from the right-hand side of our function, right, absolute value of x over x, equals to positive 1. So the left limit does exist, the right limit does exist, but they don't equal to each other. So we would say that the unrestricted limit doesn't exist, right? If we don't have that condition of only approaching from one side or the other, we need that restriction, otherwise it doesn't exist. So the left limit and the right-hand limits are not the same. Therefore, this limit does not exist. Right? Notice that here, the difference between these is that this doesn't have a little plus or a minus. That means it's unrestricted. It can approach 0 from either direction. And if you can approach 0 from either direction, you're going to get different answers. Sometimes you get a negative 1. Sometimes you get a positive 1. So that does not exist. Okay, I know this can get confusing. We're going to see some more examples. Use the graph to discuss the behavior of f of x for x equals to near negative 1. Okay, so here is our function provided for us in blue. Don't worry about what the actual equation is, right? We just have a graphical representation of our function, right? So this whole thing is f of x, right? All of it. That and this, all of it is f of x. Okay, so what happens around negative 1? So here is negative 1. And we want to know what happens as we approach negative 1. And we get to, it doesn't say to restrict it from any direction, so we have to think about it from both directions. So as x is chosen to be this point, and then later it's chosen to be this point, and then later this point, and then later this point, and then later this point, we get closer and closer and closer to negative 1 from the right-hand side. Same thing from the other direction. We let it be equal to this point, and then this point, and this point, right? As x squeezes closer to that, and we think about the outputs are all approaching the same thing, right? And it looks to me like it equals to close to positive 1, right? Just from the picture, that's what we get. So I would say that the limit as x approaches negative 1 from the right-hand side of my function f of x is equal to positive 1. And the limit as x approaches negative 1 from the left-hand side of my function f of x is also equal to 1. Because the left-hand limit exists, the right-hand limit exists, and both limits equal to the same thing, then I don't have to restrict it and say from one side or the other. I can just openly say, well, it's just the limit exists. The limit as x approaches negative 1 of f of x equals to positive 1. Okay, I know, very confusing. Takes a little bit of time and thought to get through this, right? So this is the right-hand limit. This is the left-hand limit. So the left side limit equals to 1. It exists. The left side limit exists. The right side limit exists. They both equal to 1. They equal each other. Therefore, the unrestricted limit, the limit as x approaches negative 1 from either direction, is just equal to 1. Okay, all right. So there's a nice little picture over here, I think. Here we can see a graphical representation of the same thing. As you approach negative 1 from either direction, we see that the output values are going to get closer and closer and closer to positive 1 from either direction, right? As we squeeze into the negative 1 from either direction, as x gets closer and closer to negative 1, the output values of f of x get closer and closer to positive 1 from either direction. That's what happens around negative 1. Okay, so what happens around the value of 1? Okay, so as we think about what happens here, as x is chosen to be values that are closer and closer to positive 1, so maybe we let x equal to this guy, and then later x equals this one, and then later x equals this one, and x equals that one, and we analyze the outputs seem to be getting closer and closer to positive 3 from the right-hand side. From the other direction, as x starts off there, we choose that to be our x value, and then later that one, and then later that one, and then later that one. So we're getting closer and closer and closer to 1, and we analyze the output values. They both seem to be heading in the same direction. Good. So we would say that the limit, let's start with the left side limit. Left side the limit as x approaches to positive 1 from the left-hand side. So don't confuse this to mean that this is negative 1, right? The notation is weird. Maybe I'll put a 1 this way. So don't confuse this to mean that it's a negative 1. It's not. It's positive 1 being approached from the left-hand side. That's what the little minus symbol means. Of my function f of x. Now, since they didn't give me the actual equation, I'll just have to use the notation f of x. And from the graph, I can see that it's approaching to positive 3. Good. Okay, now the right side limit. The limit as x approaches positive 1 from the right-hand side. So we're approaching from the right-hand side. I can see that my outputs are again approaching to 3. F of x equals to 3. Good. The left-hand limit exists. The right-hand limit exists. Therefore, and they exist and they give you the same value of 3. Therefore, we can drop off that subcondition that you must approach it from one direction or the other and just simply say that the limit exists. So now we can combine those two things and just say that the limit as x approaches to 1 of my function f of x equals to 3. It doesn't matter the direction. Right? So this is a more powerful statement here because you're saying it doesn't matter. It's unrestricted. You can approach it any direction you want. The limit is going to be 3. Whereas these are a weaker statement. They're saying, well, it'll equal that as long as you stick to only approaching it from the left-hand side, or it'll equal that as long as you stick to approaching it only from the right-hand side. Right? So it's a weaker statement to have a one-sided limit. But if the left side limit exists, the right side limit exists, and they equal the same value, then you can put together a stronger statement and simply say that the limit exists. And this is kind of messy. It's supposed to be LIM, not a weird squiggle like that. Erase this. The limit, LIM, as x approaches to 1 of f of x equals to 3. Okay, and again, we have a nice little graphical representation here. So as we choose values of x that get closer and closer to 1 from either direction, we come up here and we explore the outputs, and we see that the outputs are marching their way toward 3, getting closer and closer and closer to 3. So therefore, the limit as x approaches to 1 of f of x equals to 3. Right? This is a stronger statement. When you say this statement, you are already inherently saying that the left limit exists, the right limit exists, and that they equal to 3. That's the only way you can make this statement. So built into it is that the one-sided limits must be true, and they must exist and must be equal to 3. Note, however, that because there's a little hole there, this is indicating that the actual function evaluated at 1 does not exist. Right? It's undefined. I don't know what f of 1 is because there's a little hole there. Right? So it doesn't matter what it is at x equals to 1. We care about what it looks like. Where does it look like it's heading? And it looks like it's heading toward 3. We don't care what the actual value of f of 1 is. We care what happens as the function gets, as the input values of the function get closer and closer to positive 1. Care about what it looks like, not what it is. Okay? All right, let's keep going. What about around 2? Let's explore what happens around 2. So again, if we let x be some value over here that gets closer and closer and closer to 2, right? Closer and closer and closer. And we explore the output values. The output values are getting closer and closer and closer to 2. from this direction. And what about from this direction as we choose values of x that start off over here? Here's x, and then we choose another value of x, and then another one, and we get closer and closer and closer to 2. We see that those output values seem to be heading toward 5. So we can organize that by saying that the left side limit, the left limit is going to be the limit as x approaches to 2 from the left-hand side of my function f of x is equal to positive 2. And the right limit, the limit as x approaches to 2 from the right-hand side of f of x, it seems to be heading toward 5. The limit is 5. So the left-hand limit exists, it equals to 2. The right-hand limit exists, it equals to 5. They don't equal each other, so it cannot say the stronger statement of just saying the limit exists as x approaches to 2. The limit as x approaches to 2 with no restriction of f of x does not exist. Right? I can't say that it equals to 5 because it doesn't. If you approach it from a different direction, it won't. And I can't say 2 either. So we can't make the stronger statement. We'd have to settle for a weaker statement of saying, well, if you restrict it to only approaching it from the left side or from the right side, then you get a value of the limit, but you can't say the stronger statement of the value of the limit as x approaches to 2. Right? This is the unrestricted limit does not exist. Note that the actual value of the function at 2 does exist. So note that in this case, f of 2 does exist and it equals to 2. But that does not affect this. The limit as x approaches to 2 is still going to be not defined, does not exist. Okay, so again, we have a nice little graphical representation here. So as x approaches to 2 from the left-hand side only, as we get closer and closer to 2 from the left-hand side, as the input values get closer and closer to 2, and we analyze the output values are marching toward positive 2. So we get that the limit as x approaches 2 from the left-hand side of f of x equals to 2. On the other hand, as x approaches to 2 from the right-hand side, we get output values that get closer and closer and closer and closer to 5. They're marching toward 5. So the limit as x approaches to 2 from the right-hand side of f of x equals to 5. Pay attention to the notation. I know it's cumbersome and a little overwhelming at first, but it's important to keep track of the notation so that you can convey, we need good notation because the concepts, the ideas are hard, so we need good notation to express those ideas. So that is an important part of this class, to learn the notation and how to write down your ideas. Okay, so now if we leave the restriction of one side or the other side, if we look at the two-sided limit, the unrestricted limit, then that limit does not exist because the left side does not match the right side. Right? And once again, note that f of 2 equals to 2. So here we have a case where the function is defined at x equals to 2, but the limit as x approaches 2 does not exist. All right, some properties of limits. The limit as x approaches to c of k equals to k for any constant k. Right? So in other words, if the function is some constant, for example, let's say that the function f of x just equals to the number 5, right? Just some constant. Then what would this graph look like? Well, then the graph would look like this. Here is f of x. Here is x. It's just equal to 5. So it would just be a horizontal line, right? It would just look something like that. It would also go by that, y equals to 5, right? That's what that is. Okay, so now if we choose some value c, let's say c is right here. So we choose values of x that get closer and closer and closer to c. It's unrestricted, right? They don't say in which direction to approach c. So we want to approach c from every direction. So maybe we call that x sub 1, the first one chosen, x sub 2, x sub 3, maybe x sub 4, right? We march closer and closer to c from either direction. Well, because the function is just the constant 5, it doesn't really matter which direction you approach it. It's always going to be the same value, and it's always going to be the value 5, right? That's what's special about this kind of function. No matter what the input, the output is always the same value of 5. So if this was k was equal to 5, we would write down that the limit as x approaches to c of the function 5 equals 5. Right? And it doesn't matter what c is, as long as it's in the domain, then you're always going to get the same answer. And that's true for any constant. Right? That's that first rule. Okay. The second one is very similar. The limit as x approaches to c of x is equal to c. Now, what does that mean? Well, this is a very popular, very common function. It's just the function y equals to x. What does that look like? Well, if we have the function y equals to x, it's just going to be a very simple line that looks like this, right? Just this line right here. This is the line y equals to x. Right? Or y equals to f of x. Okay, so if we choose some value x equals to c, let's put it in red again, here's c, then it's going to map to that value right there. What's that value going to be? What's the output going to be? Well, it's the equation y equals to x, so that value is just going to be c, whatever it is. So like if c is 9, then it'll map to 9. If c is 10, it'll map to 10, right? It doesn't matter because it's this very straightforward equation of y equals to x equals to y, right? So they give you the same result. So now if we choose values of x that get closer and closer to c from either direction, they squeeze in from either direction. It's an unrestricted limit, right? We approach it from either direction. Well, then if we approach c from either direction, we're gonna get that the output is going to approach c from either direction as well. So that's why we get this. The limit as x approaches to c of x equals to c for any value c in the domain of our function. Good. So just to put a number out on here, for example, let's try putting in, instead of c, if we had, I don't know, arbitrarily, I'm just going to pick the number 8 here. Right? If we have this equation, y equals to x, and I plug in x equals to 8, well, then we're going to get y equals to 8. Right? So this is saying that the limit as x approaches to 8 of the function x is going to be equal to 8. Right? So these two things match. Good. Okay, so hopefully this is, these two are pretty obvious, pretty straightforward. Let's move on to a couple of other properties of limits. So let's say that it is given to us that the limit as x approaches to c of f of x equals to capital L, and the limit as x approaches to c of g of x equals to capital M, and that L and M, of course, exists, and that c is a value, that c is a value in the domain of f of x, and c is a value in the domain of g of x. So given that all those things work out, here are some straightforward properties of limits. The limit as x approaches to c of the summation of f of x plus g of x is equal to finding the limit as x approaches to c of f of x, finding that limit, which we know is L, plus finding the limit as x approaches to c of g of x, which we are told is M, and then adding them together. Right? So we can, it looks like a distribution of this thing, but it's not exactly a distribution of the limit. It's just letting you know that you can find them separately and then add them together. The limit of the sum of functions is equal to the sum of the limits of the individual functions. That's what this is saying. Okay, so we can find them separately, add them together. That's what that tells us. Same thing with subtraction. If we have the limit as x approaches to c of the difference of these two functions, then what we can do is find the limit of the f of x one, the limit of the g of x one separately, find those values, subtract their outputs, subtract their limits, and get our answer that way. Okay, I think pretty straightforward. If we have the limit as x approaches to c of some constant k times f of x, then what we could do is find the limit as x approaches to c of f of x, find that answer, and then multiply it by k. We can also think of that as factoring out the k. That's what this is saying. Good. And that's for any constant k. A couple other ones. The limit as x approaches to c of the product of two functions, f of x times g of x, as you might have guessed, we can also separate them. Find the limit of one, find the limit of the other separately, multiply them together, and that's the limit we want. Good. Same with division. If we have the limit as x approaches to c of f of x over g of x, then that's equal to a giant fraction where we find the limit as x approaches to c of f of x and then divide it by the limit as x approaches to c of g of x. So find those limits separately, divide them, and that's your answer. Only one condition, make sure that you're not accidentally dividing by 0. So this is going to be valid as long as m doesn't equal to 0. That's what that's saying. Good. And finally, if we have an nth root, of f of x, we want to find the limit as x approaches to c. This is saying that what we can do is bring the limit inside the function, the root function. So we can find the limit of the f of x function first and then apply the nth root to it, and that'll give us our result. And this is valid as long as we're not accidentally taking the even root of a negative number. Remember, that leads to imaginaries, and we don't want to work with imaginaries right now. So as long as n is odd, then L is allowed to be anything at all. Positive, negative, it doesn't matter. But if n is even, then we got to guarantee that L is going to be a positive number, right? We want to avoid taking the even root, say like a 2, the square root of negative 3, right? That leads to imaginary. That leads to imaginary numbers, and we don't want to deal with those in this class, so we're just going to avoid those. Okay, I know just rattled off 8 different properties of limits, and I think they're easy in concept to get, but of course we're not proving them. In a more advanced calculus class, we would spend a lot of time with each one of these and confirming that they make sense and that they're valid and that they are rooted in in sound mathematical reason to prove them, right? We would be able to prove them all. But in this class, we're not going to do that. So we're just going to accept them to be true and move on with our lives. So I hope they make sense. We're going to apply them and see how they work. But we're not going to worry about the proofs for these. Okay, so you're not responsible for proving that these are true. You just have to understand them and then use them with our work. So how do we use them? For example, find this limit, the limit as x approaches to 2 of x squared minus 3x. So note that we get to use our properties. I'm going to rewrite this in the following way. This is the limit as x approaches to 2. And it's really 2 different limits. The limit applies to the whole thing, not just this, right? So just to be clear, I'm going to insert parentheses here because it's all of it, the limit of this. Okay, so I'm going to rewrite it this way, the limit of, and I'm going to rewrite it as x times x minus 3x. And I'm going to use the properties that we have above. One of them says that if we have a subtraction, then we can find the limit of each one of them. So this is the limit as x approaches to 2 of x times x minus the limit as x approaches to 2 of 3x. Right? That's using the difference, this one, that if we have a subtraction of 2 different functions, then we can find them separately and then find their difference. And so I can think of this as one function and this as another function and find them separately. Also, if we have a multiplication, then we can find them separately. And so this is the limit as x approaches to 2 of x times the limit as x approaches to 2 of x minus, and now I can factor out that constant, 3 times the limit as x approaches 2 of x. Right, so we have one of our properties tells us that if we have a constant, we can bring it out like that, find the, evaluate the limit of the function x, and then bring out that constant. That's what this property right there tells us, number 5. If we have a constant, then we can evaluate the limit and then multiply it by the constant. And then the product, that would be number 6, property number 6 tells us that we can find them separately and multiply them together. Okay, so once we've done all that, well, now we can find these easily, right? The limit as x approaches to 2 of x is just going to be equal to 2. So this is just going to be equal to 2. And this is just going to be equal to 2 minus this is equal to 3 times 2. So we get that this whole limit is going to be equal to 2 times 2 minus 3 times 2, which is equal to 2 squared minus 6, which is 4 minus 6, or negative 2. Good. So we can bring it all together and say the limit as x approaches to 2 of x squared minus 3x is equal to negative 2. Good. Okay, so make sure that you use those properties very clearly and specifically in this section. They want you to walk through and identify which properties you used at every little step. So let me identify them. The first one was the difference, so that would be property 4. Let's put it in here. Prop number 4 allowed me to do that right there, separating it. And then this is prop number product. That would be this one, prop number 6. And the constant was 5. This is prop number 6, and this is prop number 5. Right? Each of those properties allowed me to make these moves. And now I knew this was true by property number 2. Property number 2 told me that. Property number 2 tells me that. Okay, so I get to bring it all together and get my answer. Okay, good. Okay, so it's not good enough on your homework or on your exam to just give me this answer here. You have to show step by step how you got each one of those and which property you used to get it. Right? I hope the homework hopefully will ask you to identify which property allows you to do each step. So hopefully you practice, but be prepared for the exam. When I do this, it'll say identify at every step which property allows you to make that step before you get to it. So just simply saying, oh, the answer was negative 2 is not going to give you any credit at all for a question like this on the exam. Okay? All right, so it'll say use the properties of limits and identify which property allowed you to do each step. All right, here's another example. So first of all, to find this limit, let's say this limit is then equal to a giant fraction just to 4 of 2x, and the limit as x approaches to 4 of 3x plus 1. Right? Which property let me do that? Well, there's a property just like that right here. Property number 7 it says if we have the limit of a division is equal to a giant division where we find the limit of the numerator, find the limit of the denominator. As long as we don't get a 0 in the denominator, we're okay. That's by prop number 7. Okay, well, we already know that when we have a constant, we can pull it out. And we know that when we have an addition, we can separate them. So let's say that this is going to be equal to 2 times the limit as x approaches to 4 of x. divided by the limit as x approaches to 4 of 3x plus the limit as x approaches to 4 of the number 1. Right? So this is the constant, one that allows you to pull out the constant. That one was property number 6, I think. No, property number 5 is the one that allows you to pull out a constant. Property number 5 is the constant. Okay, so this is, I'm allowing to separate that constant by property number 5. Prop number 5. And the property that allowed you to separate an addition, that one was property number 3, allowed you to separate an addition. Okay, and then I have the same idea of pulling out a constant. That's going to be property number 5 again. It's going to be 2 limit as x approaches to 4 of x divided by 3, the limit as x approaches to 4 of x, plus the limit as x approaches to 4 of 1. Okay, so now by property number 2, I believe, that was this one, we can see that this is going to be equal to 4. Right? This is going to be equal to 4 by property number 2. And this is going to be equal to 4 as well, again, by prop number 2. Says that that's equal to 4. And then property number 1 says that this is equal to 1. So all in all, we have that this is going to be equal to 2 times 4 divided by 3 times 4 plus 1, which is going to be equal to 8 over 12 plus 1 is 13. So bringing it all together, we'd have that the limit as x approaches to 4 of 2x over 3x plus 1 is equal to 8 over 13. Okay. I know that it's going to be tempting to jump to conclusions about how things are easy and you don't have to do it this way. I get it. You know, your goal in this class should not be to find the answer in the best and fastest and easiest way possible. You think that's the goal, but that's not the goal. The goal is to understand these ideas. So it doesn't matter that there's an easier way to do this. It matters that you follow these concepts and that you get to the same conclusion. So when the test comes around, make sure that you are able to express this whole thing over here and identify which properties allow you to do what and why, and not just come up with the answer. Good. And I know that a lot of people are going to look at this and go, well, I know, I can just plug in a 4 there and that's how I get the answer. I know you can, but that's not really the point. Okay? All right. So, some more properties. Again, we don't worry about proving them in this class. We just have to understand them, know them, love them, and move on. Okay, so as I just noted, I know some of you guys are looking at these two examples up here and you go, well, wait a minute, all you did is replace the x with a 4, and then that's how you get the answer. And then up here, same thing, all you have to do is plug in a 2 into x, and that's how you get the answer. That's true, but that wasn't the point at this stage. At this stage, there were 8 properties of limits provided, and you were supposed to identify how those properties help you find your limit. But now this new property presented to you is saying exactly what many of you were thinking. If, in fact, f of x is a polynomial, then it's true that to find the limit as x approaches to c of that polynomial, all we have to do is plug in that function into our polynomial. That's what this is saying. On the other hand, if we have a rational function, then all we have to do to find the limit as x approaches to c of the rational function r is to evaluate that rational function at c. So this is saying exactly what many of you were thinking. To find the answer here, all you have to do is plug in a 4. True. It's a rational function, plug in a 4. As long as the denominator is not 0, we're going to get the same answer. And same thing for this one. As long as we have a polynomial, we want to find the limit, all we have to do is evaluate that polynomial at that value and we'll get the limit. Okay, so for example, let's find each of these limits. So note that here we're being asked to find this limit, and this is a polynomial. Note that 2x to the 4th power minus 3x squared plus 1 is a polynomial. So if this is some function f of x, for example, we can write it down in this notation style. And so if I wanted to find the value of this function, that's f of blank, 2 blank to the 4th power minus 3 blank squared plus 1. And if I wanted to plug in a 2 into here, 2, 2, 2, 2, then f of 2 would be equal to 2 times 2 to the 4th power. 2 to the 4th power is 16 times 2 is going to be 32. Minus 4 times 3 is going to be equal to 12 plus 1. So this is going to be equal to 21. So f of 2 equals 21. 2 there and 2 there. 32 minus 12 is 20 plus 1 is 21. Okay, all right, so when we want to find this limit now, when we were doing our properties, if we want to do it by the properties, you know, using rules, properties of limits. If I said use the properties of limits, then we'd have to separate it all out. We know that if we have an addition or a subtraction, we can separate it, right? So we can say the limit as x approaches to 2 of 2x to the 4th power minus 3x squared plus 1. We go, okay, well, one of our properties says we can separate it into the limit as x approaches to 2 of 2x to the 4th power minus the limit as x approaches to 2 of 3x squared plus the limit as x approaches to 2 of the number 1. We know we can pull out constants, so we'd say that this is going to be 2 times the limit as x approaches to 2 of x to the 4th power minus 3 times the limit as x approaches to 2 of x to the 2nd power plus, well, we don't have to do anything with this one. The limit as x approaches to 2 of 1, well, we know what that one is. When our property number 1, by property number 1, we know that this is just going to be the constant 1. So we can just leave that alone. Put a 1 there. And we know that by the multiplication one, we know we can separate this into the limit as x approaches to 2 of x times the limit as x approaches to 2 of x. And each one of these is going to end up being a 2. Right? So this is going to be a 2, and this is going to be a 2. This is going to be a 2 by property number 2, but both of these. Property number 2 allows you to do that. And the property that allowed you to separate this into multiplications was property number 6, I think. Property number 6 said that if we have a multiplication, x times x, it's equal to the limit, and put an x there, put an x there. So property number 6 allowed us to separate it that way. So from here to here, this was property number 6. Prop number 6 that allowed this step. And we can do the same thing for this one where we separate it into 4 of them. Okay, so we don't want to do it this way. I'm saying that we can use the properties to expand this whole thing out. However, we were just told this new property right here indicated that the limit as x approaches to c of f of x equals to f of c for a polynomial. So all we have to do is evaluate our function at c, and we'll get the same answer. So as long as you invoke this theorem, the limit of polynomials and rational functions, limit of polynomials, you can simply say, because this is a polynomial, then all we have to do is evaluate it at that function. So we can, instead of doing all this work, we could say the limit as the limit of 2x to the fourth power minus 3x squared plus 1, that limit as x approaches to 2 is equal to f of 2. Evaluate my function at 2. That's what it equals to, because this is a polynomial. If it wasn't a polynomial, then we wouldn't be able to do that, right? Then we'd have to use the rules. This shortcut only applies to cases where we have a polynomial. Okay, well, we just did that up here. We evaluated our function at 2, and we got an answer of 21. So we can conclude that our limit as x approaches to 2 of 2x to the fourth power minus 3x squared plus 1, that limit equals to 21. Okay, another one. Find this limit. Okay, so the limit as x approaches to 1 of the cube root of this, 2x to the fourth power minus 3x squared plus 1. Okay, well, we have a property that says that what we could do is bring the limit inside the cube. So this limit is actually equal to the limit as x approaches to 1 of, is actually equal to the cube root of the limit as x approaches to 1 of 2x to the fourth power minus 3x squared plus 1, where this is a polynomial. So because it's a polynomial, all we have to do is evaluate that function at 1. This is equal to the cube root of f of 1, where f is this thing. So given that f of x is equal to 2x to the fourth power minus 3x squared plus 1. So now f of 1 means we plug in a 1 into each of those. So we get cube root of 2 times something to the fourth power minus 3 times something to the second power plus 1. We have to evaluate it at x equals to 1. That's going to be equal to 2 minus 3 plus 1. That's going to be the cube root of 2 times 1 is just going to be 2, minus 3 plus 1. And so the whole thing equals 0. So that'll be the cube root of 0, which just equals 0. Okay, so we can just bring it all together. So very often you'll see that I use notation like this. And that way, on the left-hand side, we're supposed to copy all these down. So I'll just copy it one time at the bottom here. The limit as x approaches to 1 of the cube root of 2x to the fourth power. Oh, that's messy. Erase that. X to the fourth power minus 3x squared plus 1. And the cube root of that, and it's the limit as x approaches to 1. Okay, so then I would just put like this and say, so it's the same on the left-hand side. I'm saying this equals that, equals that, equals that, all the way down, and so we get that the limit equals 0. Okay, moving on, finding this limit. Okay, so again, we know we can separate this into a giant fraction where we have the limit of the numerator, limit as x approaches to 2 of 2x plus 3 over the limit as x approaches to 2 of 3x plus 2, dot, 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 dot. We can do that using our properties of limits. However, we were just told that if it's a rational function like this one, then we can just evaluate it at that point as long as we don't have a 0 in the denominator. Right, so I put or the limit as x approaches to 2 of 2x plus 3 all over 3x plus 2 is equal to 2 times blank plus 3 all over 3 times blank plus 2, where that blank there is a 2, which then equals to 4 plus 2 is equal to 7, divided by 6 plus 2 is equal to 8. So 7/8 is our answer. Okay, so as long as we have a polynomial or a rational function, we can do it the easier way, which is just to evaluate the rational function or the polynomial at that value. Good. Okay, another example. The limit as x approaches to 4 of the absolute value of x over x. This is equal to the limit as x approaches to 4 of the absolute value of x divided by the limit as x approaches to 4 of x. And note that 4 is a positive number. And as we get closer and closer to 4, so we're thinking of numbers really close to 4, but not actually 4, like 3.9, 3.9999, or 4.001, as we come up with values really close to 4, what they all have in common is that they're all positives. Right? So as long as they're all positives, then we know that the absolute values aren't really going to do much. So we know that this limit is going to be equal to the limit as x approaches to 4 of just x. Right? So we don't worry about the absolute values because they're all positives. And the denominator, well, it's going to be the same thing, the limit as x approaches to 4 of x. So we'll just end up getting a 4 over 4, which just equals to 1. Right? This will approach 4, this will approach 4. Therefore, the whole thing divides and we get a 1. Okay, good. Let's move on. How about if we had a function defined this way? Let f of x equal to this. We have x to the 4th power, x squared plus 1, whenever x is strictly less than 2, and x minus 1 if x is strictly greater than 2. Okay, let's graph this function. X squared plus 1. So x squared plus 1, just a rough sketch of what this thing is going to look like. Let's come over here. It's going to be some parabola raised up to 1 by 1 unit. So it's going to be something that roughly looks like that. I know it's really ugly, but it's just a rough sketch. And then we have a linear equation with a slope of 1 and going through the x-intercept at -1. And also note that at x equals to 2, we get 4 plus 1 is 5. So we get something like this, 5, 2, and over here, when we put a 2, we get a 1. Okay, so if we put a 2 into here, we get a 1. So 2 gives you a 1, and it goes through the ordered pair. Okay, so that's a nice beginning. Y, x. So here, this is the equation x minus 1. It goes through the point -1, 0, -1, y-intercept of 0, -1 with a slope of 1. And then if I plug in a 2, I know that a 2 leads to 1. And then also this is a parabola raised by 1 unit. So it's a parabola raised by 1 unit. Oops, this should go all the way down to here then. That's an ugly picture. Erase. So this guy, getting a 0, we get a 1. So this guy looks like that. That's ugly. So we have that, and we have that, and okay, good. So there's like a little hole there, and there's a little hole there. Okay, so we graph the parabola, we graph the line, and now we pay attention to the domain. This is saying that when x is less than 2, we pay attention to this part of the graph. Therefore, we can erase the rest of it. So I'm going to erase this part of it over here. And when x is greater than 2, strictly greater than 2, then we only pay attention to this part of it. So we only pay attention to that. So I'm going to erase this. And of course, when x is equal to 2 exactly, it's not defined. So now this is a rough sketch, very rough sketch, of what f of x looks like. F of x is both of these pieces. F of x is both that as well as that. Right? It's the whole thing in blue, just defined by this. Okay, so based on the picture and the equation up here, we can find both of these. The limit as x approaches 2 from the left-hand side. So from the left-hand side, if I choose an x to be there, and then there, and then there, and then there, so I march my way closer to 2, but always sticking to the left-hand side, I can see from my picture that it's going to get closer and closer and closer and closer and closer to 5. Good. And then on the other hand, if I approach x from the other side, if I choose an x over here, and I get closer and closer and closer to 2, pick values that are closer and closer and closer and closer and closer and closer to 2, we see that the output values are going to get closer and closer and closer to 1. Good. So let's write those down. The limit as x approaches to 2 from the left-hand side of f of x is going to be equal to the limit as x approaches to 2 from the left-hand side. Now, from the left-hand side, it means we're only going to be following the instructions of this equation. So I can copy that down and say that it's x squared plus 1. Okay? And that's a polynomial. Poly. So that means I can just evaluate it at that number 2. So this is going to be equal to 2 squared plus 1, which gives me 4 plus 1 is 5. So I can bring that together and say that the limit as x approaches 2 from the left-hand side of f of x equals 5. Good. The limit from the right-hand side. So now the limit as x approaches to 2 from the right-hand side of f of x, that's equal to the limit as x approaches 2 from the right-hand side of x minus 1, right? Because from the right-hand side, then we only follow these instructions, right? As x is always bigger than 2, we always follow that information there, that equation. And now that's a polynomial as well. So I can just plug it in. Our rules tell us that if we want a limit and we find the limit of, if we want to find the limit of a polynomial, all we have to do is evaluate it. So we can just plug in a 2 there now. So we get 2 minus 1, which equals to 1. So I can bring that together and say that the limit as x approaches to 2 from the right-hand side of f of x is equal to 1. Okay, so that's part A, part B, part A, part B. Part C says find the limit as x approaches to 2. Well, the limit as x approaches to 2 is unrestricted. It doesn't have a left side or a right-hand side, so they mean from any direction. And we can see that the left-hand limit and the right-hand limit do not match. They don't equal each other. Therefore, the limit as x approaches to 2 does not exist. The limit as x approaches to 2 of f of x does not exist because the left-hand limit does not equal the right-hand limit. Good. And now find f of 2. Well, there's little holes there, right? There's no description here of what happens when x equals to 2. So we'd say that f of 2 is undefined or does not exist. Right? It's undefined in our function. We don't know what it is. Good? Good? Notice that a very common answer there is that it's 0. Like that does not exist. It doesn't have one, so they put 0, but that's not the same thing. 0 is an actual answer. We're saying there is no answer here. It's undefined. They didn't describe for us what happens when the input is 2 and x is equal to 2. Okay, all right, let's keep going. All right, we're going to define something called indeterminate forms of a limit. So if the limit as x approaches to c of f of x equals to 0, and the limit as x approaches to c of g of x is 0, then the limit as x approaches to c of f of x over g of x is said to be in the indeterminate form, or more specifically that it's going to be in the 0 over 0 indeterminate form. Okay, so we're trying to find the limit of this fraction, and we end up with a case of 0 divided by 0. That's when we get an indeterminate form. So the term indeterminate is used because the limit of the indeterminate form may or may not exist, right? It requires further examination, and that's what we got to spend some time thinking about. Note that the expression 0 over 0 does not represent a real number and is never used as the value of the limit, right? It doesn't mean that you found your answer. It means that more investigation is needed. We need to do some more work to figure out what that limit is. So as the following examples, if a limit is in determinate form, further investigation is required. Determine the following. Okay, so let's work with this guy. For example, if we had x squared minus 4 divided by x minus 2, what's going to happen here? Well, if we kind of proceed like normal, we have one property that tells us that we can separate this into a giant fraction where we find the limit of the numerator, the limit as x approaches to 2 of x squared minus 4, and the limit as x approaches to 2 of x minus 2. Right? One of our properties told us we're allowed to do that. And now this is a polynomial, and this is a polynomial. So based on that, because it's a polynomial, we know that we can just evaluate the function at that number. So we put a 2 there, and we put a 2 there. And then we'd end up with a 4 minus 4, which is a 0, divided by 0. This is a case where we have an indeterminate form of the form 0 over 0, right? An indeterminate form. So what do we do in this case? Well, further investigation is needed. In this case, and this won't always work, but in this case, note that the following could be true. If we have the limit as x approaches to 2 of x squared minus 4 all over x minus 2, then what we could do is we could factor the numerator. We get the limit as x approaches to 2 of x plus 2 times x minus 2 all over x minus 2. Right? Note that that's how we factor x squared minus 4. This is the difference of squares. This equals to x minus 2, x plus 2. Right? Difference of squares. Okay, now can we cancel these? Well, we can cancel them as long as we don't have a 0 divided by 0. Like, for example, if we just had x minus 2 over x minus 3, oops, sorry, minus 2. Well, actually, no, let's do blank minus blank. So we had a blank there. Blank minus 2, blank minus 2, and we input, say, a 4, put a 4 there and a 4 there, well, that's going to end up being 2 divided by 2. That just equals to 1, right? They cancel. They reduce to 1. On the other hand, okay, not a 4. How about a 9? Put a 9 there and a 9 there. Well, that turns into 7 divided by 7. That equals to 1, right? So these two will always cancel. They will reduce to 1 as long as x is not equal to 1. Right, so this 2 reduced to 1 as long as x does not equal to 2. Because if x equals to 2, then we would have a 0 divided by 0, and that's crazy. That's weird, right? But as long as we avoid that, whatever we input is going to be the same number divided by the same number. Lucky for us, though, we're only considering cases where x is approaching 2 and never actually equal to 2. We're going to be inputting numbers like 1.99, 1.9999, or 2.001, for example. And in all of those cases, these guys cancel. right? So what I'm saying is that this limit, the limit as x approaches to 2, is going to be blank plus 2, blank minus 2, divided by blank minus 2. And so the kinds of numbers we're going to be inputting to evaluate this are things that are getting close to 2, like 1.999, 1.999, 1.9999, 3 nines. Okay, in this case, these two will cancel, right? And this does not equal to 0. It's really small. It is a small decimal, but it's definitely not 0. And this are identical, so they cancel. Or on the other hand, it could be that it could be that I input something that's really close to 2, but on the other side. So this could be like a 2.001, or another 2.001, or a 2.001. Again, it's going to be a small decimal, but it's not 0. And again, this and this are going to be identical every time, so they cancel and equal to 1. So you're allowed to cancel them as long as you kind of promise never to let x equal to that 2, which is exactly what the limit is. The limit cares about what happens as you approach 2, not what happens at exactly equal to 2. Okay, so then those guys cancel, and what we have left over after that cancellation is the limit as x approaches to 2 of x plus 2, and well, that's just going to be a nice pretty polynomial. We can just input a 2 into the x, and that'll give us the answer. The limit as, oops. This is just going to be equal to blank plus 2 because it's a polynomial. So all we have to do is input that 2 from there, and so we get that the answer is 4. Okay, so we can bring it all together and say that the limit as x approaches to 2 of x squared minus 4 divided by x minus 2 is equal to 4. Good. Note, again, that if you just plugged in a 2, you would have gotten a 0 over 0. And then that's an indeterminate form an indeterminate of the form 0 over 0. But then if we do some more investigating, we see that in this case, and this won't always work, but in this case, we're able to factor the numerator, cancel something common, a common factor to the denominator, simplify our limit, and we end up with the proper answer. Okay, let's try graphing it and see what happens. So if we graph this whole thing, it's x to the 4th minus 1 over x minus 2. Let's use Desmos to graph it. X to the 2nd power minus 1 divided by x minus 2. Oh. Okay, notice that this x to the 2nd power minus 4 minus 4. There it is. X to the 2nd power minus 4 divided by x minus 2, that's this one. Well, it looks almost like a straight line, right? Let me zoom into here. And in fact, if I just graph the equation y equals to x plus 4, sorry, x plus 2, we get the exact same line. Let's put it in a different color. So the blue one, let me zoom in a little more. The blue one is the original one, the rational function x squared minus 4 divided by x minus 2. This one, that's the blue one. But then if I take that away and just graph y equals to x plus 2, I get the exact same graph, right? They're the same ones. So this is a little deceptive in that it almost looks like it's a solid one, but what you see, what happens is that if we let x equal to 2, 2 comma f of 2, well, it doesn't say, but if we plug in a 2 into here, we end up with a 0 over 0. So that's not good. It isn't like that. But if we just label 2 comma 4, like that, right there, 2 comma 4, then what we really have is that in this function, in the original function, there should be a hole there. There's a little hole right there because you cannot evaluate it there. You cannot let x equal to 2. But as we get closer and closer to 2 from both sides, we see that this whole thing approaches to 4. And we can find that because we can say that this is equal to, almost equal to, this function of just x plus 2, where this one doesn't have a hole. And this one we can easily find by letting x approach 2 from either direction. Let me clarify that over here. So what we're saying is that x plus 2 looks like this, solid line. This is the function x plus 2, like that. Solid whole line, just like that. And let's call that y and x. And here is 2. 2 leads to 4. So as x approaches 2 from either direction, we see that it's going to be equal to 4. Now, how does that compare to the rational function we're working with? Well, they almost look identical. The graph of the rational function is going to look almost like the x equals to 2. It'll be x to the second power minus 4 over x minus 2. That's that one. And it's almost that, except there is a tiny little hole right there. And I'll put this like that. There's a little hole right there at 2. And that we found out that that leads to 4. So as x approaches to 2 from either direction, we see that it approaches to 4. So this graph and this graph are going to look almost identical, except for a little hole there at 2 because of the denominator. Okay, hopefully that made sense. So we have this theorem. The limit, if the limit as x approaches to c of f of x equals to capital L, and L does not equal to 0, and the limit as x approaches to c of g of x does equal to 0, then the limit as x approaches to c of f of x over g of x does not exist. Okay, so if the numerator equals to some constant L, the limit exists, it equals to some constant L that's not 0, and the denominator does equal to 0, then we'd say that the limit does not exist. Okay, so for example, if we had the limit as x approaches to c of f of x, let's say that its limit was equal to 4. Right? Let's say the f of x is equal to 2x minus 1.
minus 2 minus, I don't know, let's make up some numbers here. Minus 3. Let's take that away here. For example, the limit as x approaches to 5, let's say, and put a 5 there, that's going to be equal to 7. So let's say we have this is 7. But now we also have some other function g of x that's just equal to x minus 5. So the limit as x approaches to 5 of this g of x function is going to be 0, right, as x approaches that. So if we have the division of the two, the limit as x approaches to 5 of f of x divided by g of x, well, this is going to be the limit as x approaches to 5 of the f of x divided by the limit as x approaches to 5 of the g of x. So we're going to have a case where the numerator is approaching the limit of this one's approaching 7, and this one's approaching 0. So we're going to end up with a case of 7 over 0, not a 0 over 0 indeterminate like before. So this is a case of the limit does not exist. Right? Does not exist. It's not a case of let's investigate some more, it might exist under certain conditions. It just doesn't exist. Okay? So a constant, it's not 0 in the numerator, and a 0 in the denominator means that the whole limit does not exist. Determine if the limit is a 0 over 0 indeterminate form, find the limit, and explain why the limit does not exist. Okay, so let's examine this one. Zoom in a little more. So we begin our investigation by separating this. I see that this is the same thing as a giant fraction where we're going to figure out the limit of the numerator, limit as x approaches to 2 of x minus 2, and then the limit as x approaches to 2 of x squared plus 4. Well, if we plug in a 2 in there, this is a polynomial, so this is just the same thing as 2 minus 2. That's going to be a 0 up in the numerator, divided by blank squared minus plus 4. We put a 2 right in there. And so this is just going to be equal to 0 divided by 4 plus 4, that's going to be 8, which equals to 0. So the limit just equals 0. This is not a case of an indeterminate form of 0 over 0, it just equals to 0. Right, so we can bring it all together and say that the limit as x approaches to 2 of x minus 2 all over x squared plus 4 equals to 0. Okay, determine if the limit is a 0, 0 indeterminate form, and find the limit, explain it does not exist. Okay, so now in this case, very similar to before, we begin by separating this as a giant fraction. Now we have the limit as x approaches to 2 of x minus 2 divided by the limit as x approaches to 2 of x squared minus 4. So again, this is going to be blank minus 2, so 2 minus 2, because it's a polynomial, I'm allowed to just plug it in, divided by something squared minus 4. We put a 2 right in there, and so now we'll have a case of 0 divided by 0. This is 0 divided by 4 minus 4 is 0. This is an indeterminate form. Right? It's undetermined. We need to do more investigation. And this is going to be similar to before. This is going to be a case where we can factor and cancel. So now we can come back over here and say that the limit as x approaches to 2 of x minus 2 all over x squared minus 4 is going to be equal to the limit as x approaches to 2 of x minus 2, and now factoring the denominator gives me an x plus 2x minus 2. And then these guys cancel because the limit as x approaches 2 means that we're not going to consider the case when x is equal to exactly 2. We're just getting close to 2. means that those guys can reduce. And so this will be equal to the limit as x approaches to 2 of 1 over x plus 2. And so now this is equal to the limit as x approaches to 2 of 1 divided by the limit as x approaches to 2 of x plus 2. We know by one of our properties of limits, we know that this is just going to be equal to 1. And we know that this is just going to be equal to 2 plus 2, which is just going to be equal to 4. Right? That's because this is a polynomial, so we can just plug it in. 2 plus 2, because it's a polynomial. And so we end up with 1 divided by 4. Okay, so we can bring that together and say that the limit as x approaches to 2 of x minus 2 all over x squared minus 4 is equal to 1/4. Okay, one more time here. Let's figure out this one. Here we have, again, we're going to begin by separating it. One big happy fraction. The limit as x approaches to 2 of x plus 2, and the limit as x approaches to 2 of x squared minus 4. That's going to be blank plus 2, so that would be 2 plus 2. That's going to be a 4 up in the numerator, divided by blank squared minus 4. So that's going to be a 4 divided by 0. So this is a does not exist. The limit does not exist. Okay, I know it's been a long section, almost done. The difference quotient. So suppose f of x is a function defined in an open interval containing a number a. One of the most important limits in calculus is the limit of the difference quotient, the limit as h approaches to 0 of f of a plus h minus f of a all over h. Okay, so let's do a little graph of what this is explaining. So let's say we have a function that just does this kind of thing here. And we have, let's say that this is the value a. We often use x, but let's use the value a. And then somewhere afterwards, somewhere over here, let's say, let's use green. We have a green there, and then that leads to some value a. And then we have some other value over here. Okay, we naturally might use some other number, say b. So therefore, this value right here would be f of a. So this is the f function. This is the f of x function in blue. So these are x values there. And here this would be f of x. So this point right in there is the result of plugging in a b into your function. So it would be f of b. Right? And then this point right in here would be f of a. So if we decided to subtract these two things, it would be the little gap here, this space, this distance between these two. That gap would be the difference between the two. And so that difference would be, that difference right there would be f of b minus f of a. Right? And then this distance here, this little gap right here, let's put it in green. That gap right there, that distance, we can refer to it as the distance b minus a. B minus a. Okay? So that distance right there is this number minus this number. Like, for example, if this was the number 13 and this was the number 7, and I wanted to find that distance right there, I would do 13 minus 7, which gives me a 6. So that would be the distance. The distance right there is 6, for example. Okay, so this is the notation we most often use, but we could introduce something a little bit different. And so the thing we're going to introduce is the idea that instead of saying this is A and then this is some other value B, what we're going to do is think about the gap between these, that gap as being the H gap, whatever it is, H. And so therefore, instead of just calling this B, we're going to call this number A plus H instead of calling it B, right? Because it's A plus the gap, A plus H. Therefore, this number here is not going to be referred to as f of B. We're going to refer to it as f of A plus H, right? And so this point right there, if you want to write down the ordered pairs, this ordered pair would be the ordered pair A plus H, comma, f of A plus H. And this point right here would be the point A, comma, f of A. Good. And so this gap right here, this distance then would be this one minus that one. So instead of writing it this way, we would write f of A plus H minus f of A. And that would describe that gap right there. Right? So that's what this is describing here. F of A plus H minus f of A. That would be describing this distance there, divided by H, where H is this. And what we want to do is consider the limit as H approaches 0. As this gap gets smaller and smaller and smaller, that means that this dot gets closer and closer and closer to this dot, and we're going to see where that is heading, right? That's the limit that we're interested in. Okay, so consider what happens to this whole fraction as H gets closer and closer to 0. As the gap between these 2 points gets smaller and smaller, right? H becomes a smaller and smaller value. Then these 2 points become closer and closer to each other. The gap gets closer and closer to 0. And then as these points get closer to each other, then these 2 points will also get closer to being the same one, right? So therefore, the gap between these two will also get closer and closer to 0. So very often, we will have the case that the numerator, the limit as h approaches to 0 of the numerator will be 0. Therefore, also, the limit as h approaches to 0 of this function will also be a case of 0 over 0, which is indeterminate. Right? Very often this will be an indeterminate form. For example, let's try an example. Find the difference quotient, this guy, when f of x is equal to 2x minus 3. So this is clearly a linear equation with a slope of 2 and a y-intercept of 0, negative 3. And we want to find out what this is. So as a rough picture to kind of get something, visualize something, we have some sort of a linear equation that might look something like that. I don't know, something like that, where this is the line f of x equals to 2x minus 3. And now we are not approaching x equals to 0. That's a very common mistake. We have x here, and we have f of x over here. So people see that and they go, okay, we're approaching 0. We're not. This is the x-axis, not the h-axis, right? So h is the gap between a and the next value, a plus h. So just as an arbitrary selection of what a could be, it could be that a is this guy. Let's put him here. Here's a. And therefore, a plus h is over here. This is a plus h. The little gap is going to be the distance there, which is h. This gap right there is h. Okay, so then if we come back up here and retrace this up, we'll get to this point, which would be f of a. And if we trace this up, we'll get to this point, which is f of a plus h. In other words, plug in a into that equation, and that's what the output is. Plug in this, a plus h, into that equation, and that will give you your output. right? And then when we subtract these two, that'll be that difference for the numerator, right? This difference right in here, this one is this, the gap between the difference between f of a plus h minus f of a. Good. Okay, so the limit as h approaches to 0 of f of a plus h minus f of a divided by h is equal to the limit as h approaches to 0 of, and now what I'm going to do is I'm going to plug in this into that one and this into that one. So the function f is double the input minus 3. So it's 2 times something minus 3 minus, and then it's 2 times something minus 3. Now we have to be careful because I'm going to wrap these in parentheses to be careful that I'm subtracting the whole thing. So it's this minus that. So it's going to be this minus this. So I have to introduce extra parentheses just to make sure that it's clear that this subtraction applies to the whole thing, not just the first term. And now I'm going to plug it in. And so for this first one, I'm going to plug in this. That's what goes right in there. And for the second one, I'm going to plug in this. That's what goes right in there. So I'll put it in green. So this would be an a plus h. And this is just going to be an a. Good. And then the whole thing is divided by h. Divided by h. Okay, now our goal is going to be to simplify, cancel, reduce, manipulate this to a point where I am no longer in the case of 0 over 0. In other words, I need to cancel out this h so that I can evaluate this limit and figure out what its result is going to be. Okay, so I'm going to distribute this to there and simplify it as best I can. So this is going to be the limit as h approaches to 0 of, this will be 2a plus 2h minus 3 minus 2a. Now being careful here, this is going to be plus 3. Divide the whole thing by h. Okay, now luckily some stuff will cancel. 2a and minus 2a reduces. And then minus 3 plus 3, those two reduce. And so the only thing that survives in the numerator is just going to be this 2h. So here, that means I end up with the limit as h approaches to 0 of 2h divided by h. And remember that as long as h is not equal to 0, we can cancel it. Like if h equals to 0.5, then we end up with 2 times 0.5 divided by 0.5. Well, okay, well, we can cancel 0.5 over 0.5, right? If h equals to 0.5. If h equals to if h equals to 0.01, they're not a 0 over 0, we can again cancel them, right? So we can always cancel the h's as long as they don't equal 0. And luckily for us, we're considering the limit as h approaches 0. We don't want h to be 0. H is never going to be 0. It's just really close to 0. That's what we're looking for. Okay, and so now this thing cancels. And we end up with 2. So the whole thing equals to 2. So let's bring it all together. So the limit as h approaches to 0 of this difference quotient for f of x equal to 2x minus 3, that's going to be equal to 2. So the limit as h approaches to 0 of f of a plus h minus f of a all over h is equal to 2 for f of x equal to 2x minus 3. Okay,
That's enough for now. Hopefully you have enough material to get through the homework set in section 2.1. If you have any trouble, then let me know. Send me an email. We can set up a Zoom meeting, or it could be, stuff we can talk about in our next class session. Have a great day.